Hello folks, my name is Mr. and today I would like to talk about convective diffusive heat transfer problem. Okay, here we go. First of all, I will start with the theoretical basis, followed by the problem description, and in the end I will talk about the numerical observations. Theoretical basis. A transport equation is a conservation equation that essentially is described by four different terms: temporal change of rate, convective term, diffusive term, and in the end, the volumetric source. For instance, in the case of an incompressible two-dimensional heat transfer problem, the energy conservation equation consists, among other things, of a term describing the temporal change of temperature. The second contribution refers to the convection phenomenon, and the third one is called diffusive term. And finally, Q describes the creation or destruction of the quantity. In mathematics, finite difference methods are numerical methods for approximating the solution of a differential equation using finite difference equations to approximate derivatives. This process is usually carried out as a first step toward making them suitable for numerical evaluations and implementation on computers. To do so, first of all, we have to consider a discrete space step and, if it's necessary, discrete time steps to describe the system, and each sampling point approximate equation is solved using boundary conditions. In this given example, the one-dimensional and continuous geometry is transformed in a discrete model consisting of n sampling points called P. Considering an equidistantly mesh, every point is delta x apart from each other. The approximation of the gradients can be determined by expressing T as Taylor expansion. After manipulating equation 1 and 2, you get expressions for the derivatives, including error terms of second order. Discretizing the convection diffusion equation on a uniform grid using central differences for both convective and diffusive terms, we get the approximation whereby the discretion error terms are omitted. The exact solution to this problem is determined by using an Euler approach where Pe is the Packard number. Notice that the Packard number gives a measure of the ratio of convective effects to diffusive ones. Description of problem. The 1D convection diffusion equation for a transported variable is sufficient to demonstrate some of the advantages and weaknesses that can be encountered with the numerical approximations outlined above. It can be written that T is the variable being transported by the flow, and U is the fluid velocity, which, for simplicity, we take as constant. The fluid density and kappa, the heat diffusivity, are also taken as constants. The left-hand side of the equation represents the transport effect of T being convected by the fluid. The right-hand side represents the molecular diffusion of T. Numerical parametric study. As you can see on the slide, my code consists of 4 subcodes and 1 main code. The main code introduces all values that are necessary to calculate solutions and return results and plots. A file called Convective Diffusive Calculation computes the solutions after selecting the desirable difference method. In the following part, the diffusive and convective term are implemented. Regarding to the convective term, it is important to differentiate between the central difference and the upwind method. Special attention needs to be paid to the upwind scheme. In this case, one-sided differences are used, whereby, depending on the flow direction, always upstream directed differences are applied. That means, if the velocity is positive, the sampling point to the left is taken into account, If the flow comes from the right side, U is negative, the right sampling point is considered, as you can see. A file called epsilon error computes the local and total error using the exact and the numerical solution. On slide number 19 you can see the distribution of temperature across the beam for different sampling points using the central difference method. As you see in this enlarged image, for higher numbers of sampling points, 41 points upwards, the numerical solution is independent from the numeric, respectively from the mesh. Epsilon is the difference between the exact and numerical solution across the investigated object. Because of higher gradients and a lower number of sampling points, the error is much higher on the right side of the beam, but in general and especially due to the small error you can conclude that the results reflect the reality. Considering the upwind difference method, you get quite similar results for the temperature distribution and the error. Also here, for higher numbers of sampling points, the numerical solution is independent from the numeric. But once the grid is reasonably fine, the first order upwind solution is not accurate as the second order central difference one. On slides 25 and 26, the temperature and the error for central upwind method as well as for omitting the convective term are plotted on the vertical axis against the length. The conclusions are the same as mentioned before. In part 3.3, the influence of the Packard number will be shown and analyzed. Notice that the Packard number gives a measure of the ratio of convective effects to the diffusive ones. At PE is equal to 5 or equal to 0.1 or equal to -3, the solutions give a good approximation to the exact results, and thereby they are satisfactory. But for instance, and especially for the central difference method, if the sampling point number is low and the Packard number is high, the value of t is negative, which implies that the solver returns unphysically unrealizable results. In the case Packard number goes to 0, the curve approximates to the distribution of the non-convective case. If PE is negative, the temperature increases. The difference between values of the upwind and the central difference method occur due to the diffuse characteristic of the upwind approximation. This tends to carry out a stabilizing influence on the numerical solution. Also, as seen, it has an adverse effect on the accuracy. The diffusive characteristic of the upwind method is also shown in the following pictures. A list of references. More information referring to numerical calculations you get from the book Computational Methods for Fluid Dynamics, published by Fratziger. Okay, that's it for today. Many thanks for your attention and goodbye.